Thank you for inviting me again. I always enjoy coming to the Brunel conferences. I always think of it as a harbinger of spring. The seasons seem to be changing for the better when the Brunel conference takes place. So it's nice to be here again. Well, this paper's with George Kapitainis and Fotis Papalias, and it's basically a fairly simple issue that hasn't really been explored fully really before, and that is how to construct impulse responses and confidence intervals from long memory persistent time series. So a fair bit of work has been done for the univariate case, but these models are quite often now used for multivariate systems. So the aim of this paper is to develop the appropriate methodology, and we find it's quite a simple way of dealing with the problems that I think is useful in practice. So the majority of this paper is concerned with constructing confidence intervals and appropriate standard errors for the impulse responses that you're generating. Obviously, these are one of the major interests in a lot of dynamic models in econometrics, and these persistent long memory processes are widely used in a lot of models in volatility in financial markets, spreads, certain other variables like inflation and so on. I'll just define some of these ideas in a moment, but basically we're thinking of very slow hyperbolic decay in some of these autocorrelations and impulse responses of these processes. The methodology is an extension of some univariate analysis in a paper that George and I published a year or so ago. And essentially, the unusual conclusion, in a way, is that it's not necessarily, if you're interested in impulse response weights or measurements, it's not necessarily worth estimating a complicated long memory model. In fact, you can get often better results from using a semi-parametric estimator in a time domain, which in the context of this multivariate system is going to be a vector order regression. A sieve is called a sieve VAR, and it's going to be involving bootstrapping. And so these methods turn out to give improved coverage rates for the impulse responses. And one of the interesting conclusions is that the method of estimating the impulse response very much depends on the lag length of the impulse response you're interested in. And this determines what kind of order VAR you use. So you actually have a hybrid method where you use certain low dimensional VARs for estimating some of the impulse responses and higher lag orders for the higher order impulse responses. So this is just I gave this an early version of this paper a couple of months ago, and somebody in the audience reasonably said to me, what does it mean by long memory or fractional integration? And the other people in the session found that a bit of a strange question, but quite honestly, it's a reasonable question. So might as well spend 30 seconds just for those of you who are not fully familiar with this. All we're dealing with here is the simplest version of a long memory process, is fractional differencing. So D is not an integer necessarily, but it's in this range it's said to be stationary and invertible. And even for less than 1, it's still, although the process will not have a finite variance, the cumulative impulse responses are still defined. And for impulse responses in a univariate system, we're really interested in these psi k parameters. And the interesting thing about these processes is that they have slow rates of hyperbolic rates of decay in all their properties, autocorrelation coefficients and impulse responses in particular. And the short memory component, if it's modeled by an ARMA model, you then get what's known as an RFEMA model, and that's sort of basic workhorse univariate time series model. So In the other paper that George and I did, we found that the different methods of estimating impulse responses could be essentially estimating a parametric model with the long memory, like an Arfima model, and then inverting it to get impulse responses. That would be one way of doing it, which seems in some sense the most obvious method. And then an alternative is to use, one other method is to estimate the long memory parameter by some semi-parametric estimator first, like local Whittle, and filter out the long memory component, and then estimate the short memory stuff as well, and then from that estimate impulse responses. Well, that has been investigated in several articles. That doesn't really work very well. And the method that did turn out to be better was a time domain high-order autoregressive approximation. I mean, the reasons for that I'll describe in a few minutes. What about the basic model we're looking at? Well, it's a multivariate system. So we're dealing with an m-dimensional vector of variables that have long memory of different orders. They could be short memory, it doesn't really matter. But we're ruling out integrated processes. And so YT is this m-dimensional vector. We're interested in estimating these m-squared impulse response coefficient matrices. And to usual normalization, that the psi 0 is the identity matrix, and then we have this condition on basically a moment condition for the multivariate system, and the innovations basically martingale difference sequences in a vector case. We are allowing for different orders of integration of all the variables in the system. So you've got a diagonal matrix with the order of differencing down the diagonal, but we are restricting the D's to be in this range. And the matrix of the short memory component is based upon this Wald decomposition coefficient matrix. And the whole system then would be psi L is this component for the lag operator in the vector case. That includes the, that's just for the short memory component. And then we, of course, the whole thing would involve this if we were to get the Wald decomposition coefficients for the vector process with long memory in it. So we're assuming that then this can be inverted to get an autoregressive, high-order autoregressive representation if you want to do that. So the success of this method is going to depend upon how well we can approximate this infinite order polynomial in the lag operator psi L, phi L, for the autoregressive representation. And quite a lot of stuff is known about the multivariate Arfima model. The basic work was in a paper by Sewell, fellow Sewell, and then Zhongqing Fan did as a paper on ET, where he has some of the theoretical properties of these systems. We use some of his results in this paper. So this is a relatively complicated model, but it has been implemented for some low-dimensional systems. So the key thing is that the Wald decomposition coefficients, or the impulse responses, have a form of hyperbolic decay, big O j to the power of d minus 1, where d is some fractional differencing parameter. So one of the difficulties with doing multivariate systems like this is you're not really interested necessarily in just the psi j's, the psi j's, but you may want to normalize that, orthogonalize it by some sort of Cholesky decomposition, as is normal when doing sort of any kind of VAR analysis. So obviously identifying assumptions for this decomposition are important when you implement it in practice. There have been some applications of this, quite a few things. Money and Output by Sewell. There's a climatic paper that I did with Zhongqing Fan on temperature data measured annually at different locations across the world, or proxies to it by things like tree rings. And all these variables are have long memory properties, the temperature, and you can generate impulse responses from that sort of system. And then the application we're looking at in this paper is a real interest rate on inflation and nominal interest rates. And that's a paper by Mark Jensen and the JMCB, where he uses a bivariate Arfima model for this, and we're one of the application of the paper is extending his work in the paper. Well, okay, so that's the sort of way multivariate Arfima models have been used and the basic setup. I now want to discuss how you would generate impulse response weights and get their standard errors. So let's think about the short memory component of the process. It's well known if you have a vector armor model, you can stack it up in a state space or companion form representation like in the first equation. So that the C matrix is basically, the interesting thing is the first M rows, the basic matrices, the basic parts of the model, and the rest of it's a bunch of identities to give you the companion form. So the parameter vector is going to include not only, it's going to be three real parts. It's going to be the M long memory parameters in each equation. It's going to be all the armor parameters in this part. N is a selection matrix, picking out the appropriate elements of the C matrix, the short memory parameters. And you've also got the unique parts of the error covariance matrix, which are important when you come to orthogonalize the system. And these cause more complexity in the standard error calculations for the system, and that's really without this. If you were interested in a non-orthogonalized system, it's far easier to deal with. Well, okay, there's quite a lot of work done on showing that limiting distribution around the true parameter estimates of this will have this asymptotic normal distribution, and obviously for a stationary invertible short memory process as well. And there's particularly work of Hosoya and Fox and Taku has detailed all that. And how do you then generate the impulse response weights? Well, you can invert the model to get the estimates of the impulse response matrices. So in this notation, the vec of this is going to be a vectorized impulse response matrix at lag j, so it's vectorizing it, and this is based upon parameter estimates theta hat, which would be MLEs of the system. And so if you were to follow the normal kind of approach, doing a delta approximation to get the distribution of these impulse responses, it's fairly straightforward to show that the vectorized quantity is root T consistent. This is the impulse response matrix vectorized at lag j for theta hat, and then around the true value of the same quantity, which is denoted by theta sub 0. Now, for dj, these d's are the matrices of the derivatives of the impulse responses with respect to the underlying parameters evaluated at true value theta 0. If you have an vector armor system, then you can derive an exact parametric expression for the d's. I did that years ago in a paper in Journal of Econometrics, and there's also work by Helmut Lukapol has done similar things in RE stat and a little bit later. So doing it for a vector armor system is not a great problem. You can have nice results on that. There are two problems with the whole approach, though, which make it practically not much good for a long memory. The first is there's no real way of getting a nice parametric expression for a long memory model. Once you've got the D parameter included, the state space representation becomes harder. You can't really use this kind of companion form representation. So that's one real problem with a sort of delta method. But the other problem that's even more important, really, is that for any kind of persistent processes, these delta approximations don't work very well. Jonathan Wright has a paper in the JBS on basically autoregressive models, and there's quite a bit of work on VARs by Lutz Kilian and Elana Pesavento and Barbara Rossi, who was here earlier today. So the delta method is unfortunately not very good when it comes to these kind of persistent processes, and so we're not going to pursue that in this context in the paper. The other issue is that, of course, you're normally going to be concerned, make it practically relevant, with some orthogonalized impulse responses. So you have to take this kind of form of the impulse response matrix. So, you know, it's an causes. I'm not going to go into how you do the identification. We're going to say we're assuming that kind of thing could be done as usual with VAR analysis, or you can have a causal structure on how the variables should be ordered. So in practice, you're going to do this kind of thing. You're vectorizing the orthogonalized impulse responses based upon theta hat, which is going to be an MLE, and or QMLE conceivably, and this is the true. I couldn't put a zero there, but it should be the true parameters theta sub 0. So this would, if you were to do the delta method, this would be the G matrix you would then have to compute. Okay, so we're not going to actually, that's how you would do it for vector armor. Once you get long memory, it causes more problems. So we're not going to actually follow that. We're going to use autoregressive approximations. And this is motivated by the univariate work we've done. So in this case, the order of the VAR could be dependent on the number of observations in the sample. So we've got P sub T is the order of the VAR, and we've extended some work of Poskett, which is about the order of these results due to Poskett, about the order of PT, a little o expression for this. And these basically you get little o t to the power of alpha, where alpha's a positive number. And this suggests that an acceptable sequence for the order of the VAR is log t to the power of alpha. In this case, alpha, the way we've done it here, alpha is greater than 1. So there's no real indication on what value of alpha would be appropriate, but we just know that this would satisfy those conditions for alpha greater than 1. So if you would, that's one way, would be to choose it from some sort of criteria like that. Another method is just to use an information criteria like BIC or AIC to determine the order of the VAR and then invert it. So there's those two different choices. Well, what we're doing is really a sieve VAR. Given a choice of PT for the order of the vector order regression, we can estimate it by just a linear projection of least squares and get the estimated coefficients, and then of course from that get the residuals in a normal manner. So given the estimated VAR, we can invert that to get the impulse response weights. So numerically that's not a great problem. And then you can orthogonalize it in this way, given appropriate square root normalization of omega. And for the bootstrap type of approach, we're recentering the residual vectors, resample with replacement from the vector, and to get the bootstrap standard errors, the bootstrap residuals rather. And given this generated sample that comes out of this, which we got stars for things used in the bootstrap, we can either estimate another VAR for this and again obtain the coefficients from least squares, invert to get the impulse response weights and so on. And repeating this enough times, B times, you build up the distribution of the impulse response estimates. So that would be for the whole matrix, psi j, we've called it. Psi, so we're calling this, the bootstrap version would be psi j star with a hash over it. So that's the basic method. We've got some, there are results that that bootstrap is valid for these kind of, for processes, and again, this result is an extension of one in a Poskett paper. And first thing is to show how this works, how it works for simulations. Obviously, it's a complicated system in the sense that to analyze this, we need all the elements of the impulse response matrix. So the way we set up the simulations is to have a VAR1 for the short memory component, and beta is going to be, this parameter here can be varied across the simulations. It generates different eigenvalues of the whole system. So the error covariance matrix has this, they're not, obviously the covariance exists between the two error terms. And then we have to select the values of the long memory parameter in a diagonal matrix DL. So beta, the short memory parameter, gives you eigenvalues of the component which is either 0.5 or 0.9. We select, so 0.9 is 0.9 is a relatively persistent part of the situation of the short memory component. We have done experiments for two values of D, 0.2 and 0.4. There wasn't that much difference, but 0.4 possibly more interesting as it's more persistent. So we've generated the simulation with 0.4 for both of the variables in the system. We've got a two-dimensional system. And then we've used information criteria, AIC, for selecting the order of the VAR. And we've also used this rule where we've taken the square of log t, that was the rule we saw was appropriate before. And of course, nothing is known how we scale this, so we used different values of c, the constant, which we've taken for these 4 different values. So in the simulation we've done, sample sizes are 250 and 500. If you were to take c as 1 here, you would end up with a VAR of order 30 and 39, so pretty high order vector order regressions. There's, given the results in univariate analysis, a bias adjustment correction that was originally suggested by one of the papers by Killian in a univariate case. We've implemented that. It turns out to make quite a difference to the quality of the results. So many of the results have this bias adjustment when you do the bootstrap, and then in the application actually base it on the from the generated Monte Carlo study. And the other method is using an information-based criteria, AIC, with the adjustment, which we've called K, in honor of Lutz Killian for the bootstrap adjustment. So that's the other method. I'll have a look at the results in a moment. Just to summarize quickly what the results are, not surprisingly, it's far easier to estimate non-orthogonalized impulse responses rather than the orthogonalized ones. So since the most interesting case in practice is orthogonalizing the system, we're focusing on this case. We've looked at the coverage rates and typically chosen 90% as the appropriate level for different lag lengths of the impulse responses, the different rates we've chosen. there's a considerable improvement from using the bias adjustment method, and this last paragraph really summarizes those two cases. I mean, it's really makes it much easier. Certainly improves the orthogonalized impulse responses by using these bias adjustments corrections. I'll show you some results in a moment, but a basic summary is this choice of lag length in the VAR is important. The scale of it is quite important. It turns out that for small values of C, you get good coverage for low order impulse responses, but poor coverage for high order impulse responses. And by low and high order, the value 10 seems to be a rule of thumb that works moderately well. When you choose C as a half or more, you get different kinds of improvement in the impulse responses. It then becomes poorer for the low order and better for the high order. Let me just go straight to some of the graphs on this. This is for a sample size of 250, and C is only 0.25, and it turns out for this, the order of the VAR is only 8 in this case. The red ones, these are the impulse responses, a 2x2 impulse response matrix. We're looking at the 1, 1, 1, 2, 2, 1, and 2, 2 elements, and the H goes up to 50. The blue one, we've got the non-bias adjusted are the red lines, and with the Killian correction, we're getting the one is with orthogonalized, one is non-orthogonalized. So the most important point of this is with this sort of low value for C, you get pretty good coverage rates at low lags, especially around here, but very declining poor performance as the lag of the impulse response increases. Then if you choose lag, C as 0.25, the situation is reversed really. You get much better performance at the high lags and poor performance at the low lags. So this kind of situation continues, and this is for C as 1. The performance at low lags is worse now, as you can see, and we're not going to. And the AIC this is based on not using the this PT rule, but it's just a information criteria. This actually using AIC is pretty bad for all the cases, and is not being pursued after that. So we just show that that's not something that's really very useful to use. And then there's some more results for bigger sample size of 500, where you get basically very similar performances, a bit better improvement. I mean, at low, this is a VAR of order 10 now, and the impulse responses coverage rate is pretty good for the low lags, again, more so than before. So, and so similar pattern, when C is 1, we get, again, good performance with the higher lags beyond about a lag of 10 for the impulse response weights. So there's also some results for when you've got more persistence in the short memory component. Maybe I should go on to, here's one case. C is 0.25, sample size of 500, short memory is pretty persistent, and this is for the similar case. Again, the blue line with the bias adjustment does pretty well. Often it deteriorates for this one, 2 at high lags, but otherwise it's quite good. So just going back to the summary of these things, So the conclusion is really that you get the AIC and other information-based criteria are not really worth using, but we have this different kind of performance based upon the value of C for the impulse responses. So what we've ended up doing is using a hybrid estimator for the impulse responses, and a hybrid refers to the fact we use different order VARs depending on which lag length of the impulse response we're trying to estimate. So for this is slightly unusual way of doing it, but we've got now, oh well, sorry about this, here's this hybrid VAR. Now this involves using a VAR of order H plus 1 for, this one, we use a value of 0.25 for C for using the impulse responses up to lag 10, and then a value of C of 0.5 for estimating them from 11 to 25. So when we do that, the blue line with the bias correction really is pretty good for most of these cases. This is only a sample size of 250 with this kind of short memory autocorrelation persistence, and then this is the coverage rate. Sorry. What's the difference? What is the difference between the fat one and that one? According to the graph, I've made a hold on a minute. Oh yes, okay. This is a slightly different way of selecting the order of the VAR. For the first 10 impulse response lags, we're using a VAR of order H plus 1. So if you're estimating an impulse response at lag 6, say, it's based on a VAR of order 7. That's another scheme we had. This probably turns out to produce slightly better estimates. So this is, in this case, it looks quite impressive. I mean, the way the blue line with a bias correction based upon this selection mechanism for the VAR generates pretty good estimates of the impulse responses. Okay, what about the some applications? The first, main application is about this Fisher effect, long-run Fisher effect with relating inflation nominal interest rates. It's basically motivated by Mark Jensen's paper in a JMCB, where he essentially used the fact that you had long memory in certainly inflation and to some extent in interest rates to assess the Fisher effect over, for different countries' data. And there's a long literature, of course, on inflation and whether it's what kind of properties it would have. And this is not an exhaustive list of all the papers on it. It's a big biased list I've given. There's a well-known paper by Andrew Rose in the Journal of Finance about real rate of interest, and which is assuming the inflation is non-stationary and unit root in it, which has been creates difficulties in interpreting the real rate of interest. And then there's several papers on long memory and inflation, which with this one in particular, and several other. And I haven't given all the other details. Like there's so many papers now with regime switching, monetary policy regimes, having different properties on inflation, and of course the time series properties of inflation have varied across sample sizes. Since the early to mid 90s, inflation looks much more I0 or stationary for most Western countries, whereas previously you had big regime changes that could be interpreted in an unstationary case. So it's there's a huge literature on how inflation behaves. Well, from the point of view of this study, we're just using the Mark Jensen's approach, and he's really interested in assessing the validity of the Fisher effect over these, over this history of data. And in terms of implementing our study, this is an interesting example because it's not really quite clear what creates the persistence in inflation. It could be, we know that long memory is a proxy for regime shifts, like from Diebold and Newby work and others. And so one of the attractions of implementing this kind of VAR procedure is we're not really interested in what has generated the data, arguing whether it's regime shifts or long memory. We're just making the most of the properties of persistence to then generate good estimates, in inverted commas, of the impulse responses and their standard errors. So to implement the methodology we have here, we've got inflation being causally prior to nominal interest rates, which seems a reasonable assumption. And we're using this scheme in the last simulations that were motivated by the last set of simulations, that the VAR is chosen of order h+1 for estimating impulse responses up to from lag 1 to 10, and subsequently on the basis of that log of the sample size squared with this as a normalization, as a constant in front of it. And probably show you the results of this. The two countries we've looked at, the US and the UK, inflation is the first variable and the nominal interest rates the second variable. Well, as expected, nominal interest rates have very persistent, their own shocks are very important, a long decay of them. I mean, as nominal interest rates, of course, are very persistent, and inflation, to its own shocks, is not quite so persistent, but there's also quite a lot of persistent behavior. The standard error confidence at 95% confidence intervals are given in broken lines around it. So you do get quite significant impulse responses up to about lag 15. Certainly for inflation, and a bit about lag 12 for nominal interest rates. The interesting one is sort of related to what's called a price puzzle, is that inflation does seem to be quite dependent on the shocks from nominal interest rates going back a long way. A very persistent effect of nominal interest rates on current inflation, and then not much effect the other way around. So that's for the US, and the fairly similar results for the UK. Here's again inflation, interest rates, and how inflation responds to lagged changes in lagged shocks in nominal interest rates. So that's one application that we have done. Another one, it's we've rather sort of bit of kind of amusement in a way. It's not an economic example, but the time series econometricians always fascinated by certain ecological data sets, and one is the mink-muskrat interaction. It's kind of as important to time series analysts as sunspots, I suppose. And this series goes back about, well, a long set of data on the annual trappings by Hudson Bay Company of mink and muskrat and in northern Canada. And some of the data comes from Saskatchewan, and some of it is spliced together. And the series has attracted attention because of the regular periodicity of the cycles of the animal populations. It's assumed that trapping activity is proportional to the population size, or trapping activity hasn't significantly changed, so that the number of animals caught is proportional to the populations. And a lot of ecologists who worked on it, Ken Wallace has written articles on it, with led to, this was an early version of a vector armor model, and so-called autoregressive final form analysis. Timo Teresverta has a nice paper in Biometrica on a canonical VAR approach for it. Tony Hall has a paper, I should have cited him, on this also in Biometrica on this series. And the interesting thing is that looking at this, when the early time series analysts worked on this series, there was a lot of dispute about whether these series were integrated or not, and whether they should be differenced, and also the level of persistence in them. Anyway, so we've actually repeated this impulse. This is fairly unusual analysis in a way. This is there's a predator-prey relationship, so that with annual data, so that mink are a predator of the muskrat. Excuse me. I don't know what happened there. So that basically, when the mink is series 1 and muskrat series 2, when the mink series increases, the following year the muskrat series declines. There's a negative shock, and that's shown in that impulse response weight. And so mink are preying on the muskrat, and muskrat population increases. Mink is supposed to increase the following year, and there's some little bit of evidence for that. So this is not a clear ordering. You don't really know any causal relationship between these variables. So doing it the other way round, you get a similar picture switched around with now again mink preying on muskrat. So again, this is kind of an analysis based on a priori not knowing very much about the structure of the series. You just know they're very persistent. Some of them can be captured by long memory, and these impulse response weights can be fairly easily computed, and the standard errors of them are given. In fact, these are slightly different. These are this is the broken line is the one from the hybrid VAR. This is one from an information-based one, which we don't want to go into. But you probably may not be able to see this, but there are standard errors based into the confidence intervals around these estimated impulse responses. So that's the basic conclusion paper. Although estimating long memory models by MLE is desirable, and that's an important thing to do, maybe also for prediction, when it comes to impulse response weights, which are an important policy tool, of course, we would advocate not bothering to estimate the long memory parameter models, just use a VAR and do this kind of decomposition, and then that seems to generate good estimates of the confidence intervals. We haven't actually checked out how the point estimates have worked. We believe they're okay, basically because they're an extension of the univariate work we've done, which turned out to generate good estimates from using the Civ VAR. So I'll leave there.